Hi there, welcome to Raylene Maths. In this video we will learn about polynomial functions. This slide tells us an overview of the knowledge and definitions, the skills, and the problem solving that we will do with polynomials. Feel free to pause it and read about it, but I'd like to just get started. To classify a polynomial, we're going to start with some number sequences. We're going to state the powers of 10 starting at 1. So if we start at 1, we multiply by 10, we multiply by 10, we multiply by 10, and so on we go. We can write this in a more compact notation using exponents, which would be 10 to the exponent 0, 10 to the exponent 1, 10 to the exponent 2, 10 to the exponent 3, and so on. We can do the same thing for the powers of 2 starting at 1. We start at 1, we double, we double, we double, and so on. And again, we have a more compact notation using 2 to each exponent. 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 cubed or 2 to the exponent 3 is 8, and so on. So we can talk about the powers of x starting at 1, and they would be the powers 1 multiplied by x, and away we go. And so these values, the overall term of a base raised to an exponent is called a power. I'm just going to write that down here. Base raised to an exponent is a power. And when we come up with a polynomial function, we're talking about different powers of x with different coefficients. So let's just take a look at a graph. I can have a graph of y equal to 1. I could add x. I could add x squared. And I can keep adding these power of x terms and creating polynomials. Now, I can also take these terms and multiply them by different coefficients. So, for example, y equal to negative 2x to the 5 plus 3x squared minus 7x plus 4 is a polynomial. Now, I can't see it very well, and it's not doing much interesting behavior, but there's lots of polynomials. Let's try another one. Y equals negative 2x cubed plus x. And so we get all these different shapes of polynomials, and this is the kind of class of family that we're going to be looking at. We can zoom in on a polynomial, and we can see some behavior like x-intercepts, y-intercepts, and turning points, local minimum points and local maximum. We call these local because they are the highest points or the lowest points in their nearby region. But there might be other points, well indeed there will be other points on a polynomial that will be higher or lower. And so that's really talking about the end behavior. If we zoom out, we see that as we go more to the left, or as x approaches negative infinity, in this particular case the graph goes up. So the heights on the graph are approaching infinity. And then as x goes towards the right, the graph goes down. So we will characterize different polynomials by their end behavior. Okay, so let's just take a look. Here we can classify a polynomial, and we do it by identifying the degree of the term, and the degree of a term represents, or is represented by the highest exponent of that term, or the exponent on that term. So it's the exponent on x. And so we take a look at the first term, which is 5x to the 4, and that would be our quartic or degree 4 term. And so the coefficient is 5, and the exponent or the degree is 4. The next term is the cubic term, and it involves the sign as well as the coefficient, the x and the exponent. The coefficient is negative 7, and the degree of the term, or the exponent on x, is 3. The quadratic term is the term involving x squared, and so it's a degree 2 term. Its coefficient is just positive 1, and so the term is positive 1x squared, or simply x squared. The linear term is the term involving x to the exponent 1, and that would be negative 8x. The coefficient is negative 8, and the exponent is 1. And lastly, we have a term of positive 9. The positive 9 is a constant term, and because there is no x, which is a variable, we don't have the ability for that term to vary. So able to vary is another way of saying a variable or variable. So the constant term has no variable. So the coefficient is just the same as the term itself, and the degree of this would be 0, because we would end up having 9x to the exponent 0 and x to the exponent 0 is equal to 1. So here we have different classification of the standard form of a polynomial. To be in standard form, the polynomial terms decrease in degree. So we lead with the highest degree or the highest exponent on x term. And so in this case, our leading term of the polynomial is the term that gives the name or the type of this polynomial overall. The leading term is 5x to the 4, and therefore the polynomial p of x is said to be a quartic, like a quartet, a degree 4 polynomial. So we've got a degree 4 polynomial, so we call it a quartic. We have other words for other degrees of polynomials, and we're going to classify some polynomials in the next example. Okay, here we are going to fill in the blanks or fill in the table based on the word bank. We've got several different polynomial types here, and you're going to fill in each column based on the degree, which is the exponent on the highest or the leading term of the polynomial, and then the name based on the degree, the number of terms, and the name based on the number of terms. I'm going to pause the video, so take a moment to fill in the table and then replay the video to see how you did. Here are the answers. How did you do? Just check the definitions and the words that you're using. Make sure that you've put the polynomial in standard form and that you understand the terms of how we name or classify a polynomial based on the degree of the polynomial and based on the number of terms of the polynomial. In this exercise, we are asked to express the number 12,345 as a polynomial function that is evaluated for x equal to 10. So we can break apart the number 12,345 as 10,000 plus 2 times 1,000 plus 3 times 100 plus 4 times 10 and then plus 5 times 1. And we can see these as powers of 10 that we saw earlier. Indeed, this is 10 to the exponent of 4, so it's actually 1 times 10 to the 4. And then we have 2 times 10 to the exponent 3, plus 3 times 10 to the exponent 2, plus 4 times 10 to the exponent 1, and then just plus 5, or plus 5 times 10 to the exponent 0. So we have a quartic, cubic, quadratic, linear, and constant. Now, to see this as a polynomial function, we want to have an x in here. And so we want to replace 10 with x. So everywhere we have a 10, we are going to replace with x. This is kind of like a reverse substitution. And so we are going to see that we have a polynomial of x, which is 1x to the 4, or just x to the 4, plus 2x to the 3. I can actually move this so that it lines up a little bit better. Then we have plus 3x to the 2, plus 4x to the 1, and then plus 5x to the 0. And so our polynomial, if I just write it a little bit more compactly, is a quartic polynomial with 5 terms. Now we can substitute different values for x and we won't get the number 12,345. We get these numbers because our numbers are based on 10, and here we see that 10 is the base of the exponent. So this is just a very practical example of polynomials, specifically when x has been substituted as 10. In the next example, we want to write the polynomial in standard form and classify it by degree and number of terms. So we can call this polynomial p of x for polynomial of x, or we could call it y, or we could just leave it as a collection of terms, an expression. As soon as we involve p of x or y, we are talking about a polynomial function, but otherwise we would just be talking about a polynomial expression, which we could just call a polynomial. So then let's just put the terms in descending order of degree. So we find that the highest exponent on x is 4, and so our leading term is 5x to the 4. So I'll just write that again here, leading term. And that would involve any positive or negative sign. In this case, the term has a positive sign. Then we have plus 3x cubed, and we have minus x. So that expression is our polynomial, and as soon as we let that equal y, or p of x, the whole thing is a polynomial function. Then the degree of the polynomial is the leading exponent, or the exponent on the leading term, so we have a degree of 4. And we could classify that by saying we have a quartic polynomial, 4 from the word quartet, meaning 4, and then the number of terms. In this particular case, we only have 3 terms, and so we could call this a trinomial. So we have a quartic trinomial polynomial. We don't need to say trinomial polynomial, we can just call it a trinomial. Another way of classifying polynomials is by the end behavior. So these 4 polynomials all have different end behaviors. As x goes to the left, y goes up, and as x goes to the right, y goes up. But that's the opposite scenario for the second polynomial. As x goes to the left, y goes down, and as x goes to the right, y goes down. Meanwhile, the last two, y goes in opposite directions. So here x goes left and y goes down, and y goes right on the other end. And we have the opposite scenario here. Let's take a look at our last graph. We had y equals negative 2x cubed plus x. And so the end behavior said that as x goes to the left, y goes up, and as x goes to the right, y goes down. We can take a look at another polynomial with the same leading term, so another cubic polynomial. I'll make it in blue. And we can see that different behaviors happen. So let me maybe make it negative 2x cubed plus x squared. We've got different behaviors happening here. Maybe if I made this minus, it doesn't like that, minus 4x squared plus x, let's do something like that, we get a very different shape behavior. But that's only when we are zoomed in, when we're looking locally. We have different x-intercepts, we have different turning points, we have different y-intercept, perhaps, maybe not in this case. But if we zoom out, and it gets hard to see because we've got this grid coming on, I'm going to turn off the grid. And I'm going to actually change the window dimensions a little bit. I'm going to make us go to, let's say, 1,000 and negative 1,000 for the y values. And when we do that, we can start to see that as we zoom out, the graphs look more and more alike, which means that they have the same end behavior. In other words, the end behavior is characterized not by the lower degree or the lower order terms, but the leading terms. And so we are going to group like polynomials with the same leading term behavior by classifying the end behavior. So here we have 4 polynomials, each with different end behavior. Pause the video and fill in the blanks to see how you get on, and then unpause the video to check your answers. Okay, so in each case, we've been able to identify if the graph on the left or the right is going up or down. So in the first case, as x goes towards negative infinity, y is going up, so y goes towards positive infinity. And then as x goes towards positive infinity, y also goes towards positive infinity. So this is left and up, and right and up. And so we summarize those words with this new notation. X approaches negative infinity, meaning going to the left, and then y approaches negative infinity. So if we separate this negative infinity for x and positive infinity for y, we're saying left and up. And then combining that, we're following or tracing the path along the curve here. So this is 2 things or 2 directions occurring simultaneously, and this is the separation of x going to the left while simultaneously y goes up. So we've done the same for all of the other ones. And just take a moment to check your work to see how everything fits into place, and then we'll check our understanding with an example. Okay, so just as a reminder of this notation, we're going to write whether x approaches infinity or negative infinity and what y does. So going left means that x is approaching negative infinity, while going right means x approaches positive infinity. Going up is a vertical motion, so y is approaching positive infinity, and going down, y approaches negative infinity. So this is just a new notation, and the arrow means approaches. So in number 4, we have some different polynomials, and we're going to focus on the leading term. Here we see that we have a degree 2 polynomial, and so for both of our even polynomials, the ends went in the same direction. So by even polynomial, I mean even leading term degree. So the degree of the polynomial is even. So here we have an even degree polynomial because the degree is 2, and the coefficient is negative, which means that we are going to have the shape looking like this. Now I don't know exactly where those ends are going to be, but I'm just going to draw something like that to indicate the end behavior. So pause the video and try the other three, and then unpause it to check your answers. Okay, I've highlighted the leading term in each polynomial. Don't assume that the leading term is the first term. So in the case of the third graph, or the third equation, the leading term is actually at the end. So once we identify the leading term, we can identify the degree and the coefficient. When the degree of the leading term is even and the coefficient is negative, both ends go down. In the second polynomial, the leading term is 5x to the 100, so the degree is an even exponent of 100, and the coefficient is a positive number. So both ends are going up. So here we would say as x approaches negative infinity, y approaches infinity, and as x approaches positive infinity, y also approaches positive infinity. So we can characterize that for each of these. Here, as x approaches negative infinity, y approaches negative infinity, and as x approaches positive infinity, y approaches negative infinity. So we're really just looking at left, up, right, and down. So this is left and down and right and down, characterized by these kind of approaching notation symbols. So here we have as x approaches negative infinity, y approaches positive infinity, but as x approaches positive infinity, y is going down, so y approaches negative infinity. And here the two end behavior shapes look like this, and so as x approaches negative infinity, as x goes to the left, y goes down, so y approaches positive infinity, and as x approaches positive infinity, y approaches, we go right and up. Another way that we can classify polynomials is through their tables of values, or numerically. In this case, we're going to come up with a table of finite differences. We're going to fill in the y-coordinates for each polynomial, and then we're going to calculate the changes in y, or the differences. And sometimes we might do a second change in y. So go ahead and fill in the table of values for each of these polynomials, and then look at the finite differences. So pause the video, fill in the values for y for each polynomial, and then let's check in again about the finite differences. So now we have the y-coordinates for the linear, the quadratic, and the cubic polynomials. The next step is to calculate the change in y, and change in y is represented as delta y. So we're going to take the later y-coordinate minus the earlier. Negative 6 minus negative 10 is negative 6 plus 10, which gives us a difference of positive 4. Then negative 2 minus negative 6 is negative 2 plus 6, which is 4. And as we go through, 2 minus negative 2 is 4, 6 minus 2 is 4, 10 minus 6 is 4, and 14 minus 10 is 4, we see that the first difference, delta y1, is constant. And so this is going to be true for linear functions. In fact, we have a definition for this. We also know that the change in x is constantly 1, and so the change in y divided by the change in x is a very familiar thing that we know to be the slope. So in this particular case, the delta y over the constant delta x gives us our constant slope. Now let's go ahead and do the change of y for the next two functions. Negative 2 minus negative 11 is negative 2 plus 11, which is 9. 1 minus negative 2 is 3. Negative 2 minus 1 is negative 3. So I'm going to have you pause the video and go through calculating the rest of the finite differences for the quadratic and for the cubic functions. The goal is to keep taking finite differences until you come up with a constant. And so we already came up with a constant for the linear after one finite difference. If we see that we don't have a constant finite difference yet, we would come up with another finite difference of 3 minus 9, which is negative 6. And then the next one, negative 3 minus 3 is negative 6. So go ahead, pause the video, and fill in the rest of the table, and then look for a connection between the finite differences and the type of polynomial that we have. Okay, now we've taken a look at all of the finite differences. We see that for the linear term, or the linear polynomial, it took one subtraction or finite difference calculation to come up with a constant delta y, and that's telling us that we have an exponent of 1 on the x, so we have a linear polynomial. For the quadratic, it took two calculations of finite differences, and so we know that when we come up with a polynomial whose second finite difference is constant, we have a quadratic polynomial. And in the final case, when we have a third finite difference which is constant, we end up having a cubic polynomial. So that's our connection here. Just summarize this. The number of finite differences it takes to be constant is the same as the degree of the polynomial. And so summarize that in your own words. And we're going to do a little bit more work with tables of values and modeling polynomials. Let's take a look at 3 exercises that involve tables of values and modeling polynomial functions. So here we have a polynomial function generated by the following data. We want to predict the degree of the polynomial, so we would go ahead and work out the finite differences again and determine how many times we need to take the finite difference before we get a constant. Once we know the degree of the polynomial, we can come up with a regression equation. So I'm actually going to go back and do this type of problem using Desmos, but for the previous set of data that we had, let's say for this cubic polynomial. Then we can use the same ideas for number 6 and for number 7. And then we can discuss these questions later on. So let's just take our table of values for y equals x cubed and come up with how to make the table in Desmos and how to come up with the regression equation. So for our table, we have some x values and some y values. Let's just say, I'm not sure exactly which numbers they were, I'll just put in a few values here. In fact, I'm going to slightly modify the table of values. And I'm going to make it a slightly different function then. Okay, so we've got a table of values here, and we can come up with a scatter plot. We want to set the window dimensions so that we can see all of the x and the y values. So I'm going to go a little bit to the left of the smallest x value, and a little bit to the right of the biggest x value. And then I might make my step size something reasonable. Let's say x equal to 1, or a step of 1. And then I want to go smaller than my smallest y value, so maybe to negative 30, or maybe even negative 50, and then bigger than my biggest y value. 26, you could go to 30, you could go to 50, and maybe I would increase by 10 here. So I also see that I've got these extra grid lines. I'm going to turn off the minor grid lines. And we could turn on the arrows for the grid if we wanted to see them. We could also label x and y for the x and the y axes. Okay, so here we have a scatter plot, and we would do the finite differences to know it takes 3 subtractions, or 3 delta y's, before we came up with a constant, and therefore we have a cubic polynomial. So now we are going to tell Desmos, or the regression calculator, to come up with a cubic model. So I'm going to relate y1 with the x1, and I'm going to use this tilde key, or tilde key, and I need to make a cubic polynomial, so something that's a times x1 to the exponent 3. Now remember, we need to type in x1 to relate to the x1 data values. And then we have plus b times x1 squared, plus c times x1 to the exponent 1, and then plus a constant term d. And we notice here that the statistics tell us that r squared, which is the measure of how well this red curve fits the green data, that value is equal to 1, which says that this is actually a perfect fit. In fact, as I was making up the table of values, I was calculating the y-coordinates from the equation that I had in my head. And so what we really have for our equation, I want to write it again without the y1 and the x1 by substituting the values for a, b, and c. So I have y equals 1 times x cubed, that should be a cubed, plus 0x squared plus 0x plus plus d, which is a negative 1. So we get x cubed minus 1, and I'm just going to make that the red graph, and I'm going to turn off the regression equation. Didn't mean to undo it, so I'm just going to turn off the color. I might want to use that later on. And so I see that I have the graph fitting through here. So from the graph, we could make other predictions. We could substitute y equal to, let's say, 8, and we could find some points of intersection, for example. So this is what you're going to do with the remaining questions for 5, 6, and 7, and then answer the questions based on the regression equation that you come up with. In the remainder of the unit, we will look at solving polynomial equations, graphing polynomials, and modeling and solving real-world problems. Thanks for checking out Raylene Maths.